Okay, welcome to my second video doing day 24 of Advent of Code. So last night, I took a look at the problem and this problem is all about there's some virtual machine. Ooh, sorry, let me just. Isn't that better? There's this virtual machine, and we are trying to figure out what input can generate a particular output, right? Of course, part of the issue with this problem, all approaches to this are really going to depend on the conceit of Advent of Code, which is that these problems are soluble, because the more general problem of figure out what input can be put into some fairly opaque computer program to generate a particular output, that is not an easy problem in general. In fact, cryptography is based precisely on the fact that even when the program is easy to understand, you can't necessarily do it. So trying to find a general purpose solution to this problem might not be the best approach. And in fact, I realized last night, because I was hand simulating it, and then what I started writing was something to do what I was doing to hand simulate it. And I realized this is stupid. If we were in day 12 of Advent of Code, some years, 2 or 3 years at least, Eric has had us build these virtual machines, and then on subsequent days we added additional instructions. We're on day 24, so building a virtual machine is clearly a waste of time because we are only ever going to run one problem through this machine. I assume. I don't know what's in part 2, but so it seems ridiculous to to invest all this in this weird machine and in this weird set of machine instructions, when in fact I can easily translate these machine instructions into something much more high level by hand, right? I think. But anyway, that's what I think I probably should have started with instead of just hand simulated. Actually, because in previous years, some of them I actually did this by just kind of opened a window of the machine instructions, and then I kind of typed some Python beside it and tried to, make them line up. And eventually I had written a little Python program that did exactly what the original thing did, and that was much easier for me to reason about in my head. And I do think I am going to need to do some reasoning in my head. But let's just talk about what I was starting to build last night, because I still think it's clever and fun and interesting, and I kind of wish Eric had produced a problem that required it. Maybe part 2 will require all this nonsense, but it's a lot of work that I cut out for myself that doesn't even necessarily get you to the finish line. Because the idea was that we were going to, normally each register holds a particular value. But when you have variables, because these input things are variables, instead, one approach is to, instead of holding an actual value, you hold an expression that gets built up, and it's dependent on all the other variables in the program. And by the time you get to the end of this whole thing, you have some quite complex algebraic expression. You can just try and solve it as an algebraic expression, right? And I was thinking this expression library. See, I did a bunch of clever stuff here, trying to say, well, if it's constant, let's not do that. I think one approach I could have taken is these expressions. There are constants that we know about, and then arbitrary expressions of other types, and then variables. But we could actually have an expression recursively figure out the possible values it could take, the minimum and maximum values, for example, just to get us far enough along to knowing whether two expressions are equal. because sometimes you don't know what values they have, but it's pretty straightforward to prove that they couldn't possibly be equal. I mean, just in my little hand simulation of this thing, we had realized that because digits always have to be between 1 and 9, if you take one of these digits and then add 26 to it, it's clearly not going to be less, it's not going to be equal to 1 or something. So, yes, I thought you could do all that, but you still would have some branching, because you'd have this equal instruction that I hadn't implemented yet, where you say, if these two things are equal, then take this branch, and if they're not, then do the other. And I had looked through the program, and there are only, a half dozen of those. They generally seem to come in pairs for whatever reason. And given there are only half dozen, there can only be a handful of, we can only get to hundreds or thousands of possible branches. And the point was that when we hit one of these branch points, we make a recursive call to this, evaluation routine. We say, okay, assume that they are equal. Then that actually allows us to lock down the values a lot more tightly. So, it compresses all our expressions in that branch. Go and figure out what the final expression is there, and then in this branch, consider that they're not equal. And that also, I guess, I don't know if that would let us bound our expression space, but then we just continue. So every branch just, Anyway, that was a super interesting approach. I kind of hope we don't have to go back to that for part 2, but I think, in the light of day, I don't think that's the right approach. I think I should be translating the program into something more readable and then using my brain to figure out what's going on here. So, if we believe that, then let's at least try that, because I didn't even really try. I was hand simulating to try and understand it, but in particular, it was quite repetitive, wasn't it? We did the input thing. Okay, and then it was about 20 lines of code. Then another input, mul, add. See, I think there's a regularity to this program. So, let's do a little texting. Okay. I'm going to use can you read that? I don't know if you can read that. I guess I have to. I don't want to make it big. I'm sorry. This is for me, not for you. So, because I'm going to say, okay, so we have these first things, right? Oh, well, I don't want that. So if we just, everything down to line, so the first 18 lines, right? If we copy that, then if I compare, I'm not using diff tools, I'm just eyeballing it. So it looks like the second 18 lines are exactly the same. W0025. Oh no, the only difference is this add Y1516. Okay, so that's on line... So we have the only difference between the first 18 lines and the second 18 lines is that on line 16, in the first part, y is 15, and in the second part, it's y16. Okay, and then it repeats again at line 37. So let's line that up. And 26, 1. Ooh, now we have a difference on line 6 where it's the same instruction, but we had been x plus 13 on the first 2 times, and now it's x plus, where are we? 10 on the 3rd time. Right? And then it's all the same until the y's. It was y plus 15, y plus 16, and then y plus 4 on our 3rd one. And each of these is broken by an input, so I guess we're going to have 14 of these stanzas. So we can look at 14 things by hand, right? So 0z 26 1, and then it's 15 x plus 15 instead of 13 or 10. W 0 25 x1 y 0 w, and then y plus 15. So that's 4. I think, yeah. Okay. And then we do it. So this is our 5th iteration of these 18 lines. Let's line those up. Now there is something new here, isn't there? Now, after we after we do that, we divide z by 26 instead of 1. So z, in the previous ones, yeah, we had been dividing z by 1. And now we're dividing z by 26. So z over 1, over 1, over 1, over 1, and now it's over 26. So that's interesting. And x this time is, oh, and what line was that, just so I know? So that's on line 5. See, I'm just keeping track here on my little piece of paper of what the values are for each of these things. And so we're going to see what things accumulate. We're on number 5. Let's at least get to number 7, because then we're halfway through, right? And then on the 5th iteration, x is a negative 8. Everything else is the same up to, and then this time y gets 1. Okay, and then we have another iteration. Again, we divide z by 26 this time. X gets negative 10. Everything else looks the same. And y is plus 15. Let's do, so 1, 2, 3, 4, 5, 6. Let's do the 7th iteration. Is 0z 26 1. Oh, now we're back to dividing by 1 for z. X gets 11. Those are all the same. And y is 1. Oh no, I've written down my records incorrectly. No, because this, sorry, x was minus 10. Oh, minus 10. And now x is plus 11. And y is plus 1. Right. So 4, 5, 6, 7. Okay. And everything else is the same. Should I keep going and do all 14, I guess? Why not? There might be additional changes. Let's see if this stanza changes. This time it is div z by 1 for number 8. No, div z by 26. Always look at the left is what I'm writing down. X minus 3. And yeah, all those are the same. And y plus 3. Okay, that's 8. Let's go for 9. is div z by 1. X is plus 14. And everything is the same up until y plus 3. Right? 10th iteration. Div z by 26. X minus 4. All the same. Y plus 7. Yep, okay. 11th iteration. Div z by 1. X plus 14. Oh, x plus 14, yeah. And then all the same. All the same, y plus 5. I'm worried I wrote down y incorrectly on iteration 6, but let's ignore that for now. Let's highlight that as a potential problem. Just because I have a habit of looking at the wrong window, and that's the only value where I looked at where the value of what I wrote down is the same as the right window. So let's actually change this to what? No. Foo. Ooh. Okay. So what if we said that this was Z1 X14 Y5? Yes, okay, so I got those down. So now let's do 4, 8, 10, 11. So this is number 12 that we're doing. And that all looks, Z is 26. X is minus 5. And Y is 13. Okay. 13th iteration. Oh, it doesn't match up anymore because we're run out of input, so I gotta move it. Okay. So Z is 26 again. X is minus 8. Everything else is the same, and Y is plus 3. And our last time through, we have Z is 26. X is minus 11. And everything else is the same. Y is plus 10. What? Sorry, X is minus 11. Y is plus 10. Okay, so we have 14 numbers for those variables. Let's actually name them something better. A, B, and C. Isn't that clever? So now we just have to translate this, right? So, and I can make this big for you, right? So we know we have 3 variables, plus we're reading these digits, right? So let's for D in digits, right? Well, we can indent as we go, right? Because we're doing this 14 times. So x is 0, x is z, x equals z mod 26, right? That's what those first three lines do. Z equal A, which is always either 26 or 1. Good. Okay, we can actually put this up here. 26 plus B, whatever B happens to be. Okay, so now we have this branch. So if D equals X, that sets X to 1, right? And if X is 1, then it turns to 0. And if it's 0, it turns to 1. So I think this amounts to that. Where is X? And then multiply, right. So this multiply X by Y means that Y is going to be 0 unless that condition is true. So Y equals 25. Right, and then, well, okay, we might need to actually simplify this. Y equals 0, Y equals 25, Y plus equals 1. And I claim we've now encoded all that, including our branches. Oh, and so Y, okay, and then we're getting rid of Y after this. So if we multiply Z by Y, it's a no-op. Z by 1, it's a no-op. So Z times equals 26. That's the effect of all that, right? Yeah, I think I'm good. Okay. Y equals D plus our variable wait, what was X? We had been using X. Multiply Y. Oh, okay. Y equals D plus C. Y equals D plus C. Okay. This is again, so this goes in that conditional, and we say plus D plus C. Okay. So I think that's what our block does. So, what have we learned from this? I don't know. It's succinct though, so we can reason about it. So for every digit, X oh no, oh, this was Z equals Z times 26 plus D plus C. Let's not get confused about that. because that would be a disaster. Times 26 plus D plus C digit. And what is the C here? Oh, I've forgotten which. A. Darn it! I've forgotten which was A, which was B, and which was C. That's terrible. Oh no. Let's hold on. Save that in our let's save that, and then let's undo until we get back to remembering what's what. Okay, so these are C, are the Z's. No, they're not. A's are the Z's. B's are the X's. And Y's are the C's. Okay. Now, let's redo all of our cleverness, right? Okay. So, what was I trying to figure out? I was trying to figure out what C was. C is always in a positive number between 1 and 16. Right? 1 and 16. And that seems relevant because it's less than 26. Because there's something about 26 which, little known fact, number of letters in the alphabet. Maybe that will matter. So what do we need? Well, in the end, we want Z to be 0. So what is, so X, Z percent 20. So in what situation does Z end up as 0? So D is always positive. C is always positive. How does Z ever get to be negative? How can Z ever be 0? I must have mistranslated this, right? Because Z is, I mean, it's not increasing, but it can never. Well, we do divide it by 26 a bunch of times. So I guess if Z were less than 26 and we divided it by 26, right? So, and we do that a bunch of times. So that must be, oh, apologies, my whole setup is a little weird. So if we, so what we need on our last iteration, I'm going to go to okay, so this is what I have in terms of my detailed and brilliant notes so far. So, at some point, maybe I'll figure out how to take notes on an iPad and put them on my screen, for all the future videos that I put up, because clearly this is a new career opportunity for me, because these are amazing entertainment. My audience must be thrilled. So on the last iteration, we want two things to be the case. We want Z to be less than 26 going in. And we want D is not equal, and D to be equal to Z. D is equal to Yeah. Z percent 26, which we know is just Z, right? Because we want both these things. Z plus B, and B on the last iteration is minus 11. So our last digit is, well, no, that's interesting. So Z, minus 11. So the biggest last digit we can have, irrespective of all the other ways we need to get there, so Z can be at most 25, and 25 minus 11 is 14. Oh, no, that doesn't help us at all, does it? So what, yeah. So digit is equal, so yeah, so D could be 9 and Z is just bigger. Okay, so the main thing, so if we knew, so the main thing is just Z has to be something, well, no, hold on. So in the last iteration, what? Z has to be less than 26, I said that. And the digit is Z minus 11. So Z has to be, on the last iteration, between 12 and 12 plus 9 plus 8. 12 plus 8 is 20. Okay. So we want Z to be between 12 and 20 on the last iteration, right? So, so that's after 13 cycles. So if Z is going to be between 12 and 20, then it can't be 1 on the previous cycle because D and C are both positive. So on the second to last cycle, okay, entering 14, Z has to be between 12 and 20. Entering 13, we know that Z has to be less than 26. So the division comes out to 0. Right? Oh no, that's not true. Oh. Well, I don't. What am I doing? Do I have a strategy for figuring this out? So we know that Z is between 12 and 20 on the last iteration. If it's between 12 and 20 on the last iteration, we know that we can compute it, and if it's 20, then we can plug a 9, which is the biggest number. Well, the biggest digit. So in the prior iteration, we need either Z is less than, okay, what is C on the prior iteration? Okay, on the prior iteration, if Z is greater than 26, then if Z is greater than 26, then D has to be Z percent 26 plus minus 8. Oh, we don't need this line at all. Um, well, so we effectively have 4 lines of code. Can we how do so the trick is now how do we reverse those 4 lines of code, right? Because we're effectively saying that this is forget the Verdine digits. We say next z, and it takes in a z, an a, a b, and a c, and it produces an int, right? So then let that I mean this is useless, but fine. Modify z. D is not. Oh. Next z. D. Yeah. Right? And what we really want to do is say, well, it's something like prev z from z prev, and the final z, a, b, c. These are things we all know. And then we effectively want a pair of z int and d int. You know, what are the possible priors that could have led us there? So sorry, then we want because there might be multiple priors, right? So well, okay, if so we do want to do it backwards. So if come on, think better. So well, let's just z minus d minus c over 26. So prev z prev z if d equals prev z, so that's mod 26. Oh no, sorry. Z sorry, Z on line 5. So let's call that Z5, right? No, 6. Z Z before line 4 equals Z41 actually is Z6 times A. Var Z42 is Z times A, right? There are two possibilities there. All this is very quick to compute. So that means that X is Z41 sorry, yeah, percent 26 plus B. So if D is Z40, yeah, is Z41, okay, now if Z is not equal to that, then append Z41 DD, right? Else luckily we can test this because these functions are going to be inverse of each other, because I'm sure I'm getting this wrong, but else append Z42 for D, right? But there's something very wrong here because we're saying that there is a... Oh, but the point is Z starts at 0 at the entire thing. So we need to consider the chains that lead us all the way back to 0, don't we? So we have 14 of these branches of 9. So that's not acceptable. That's not acceptable at all. So merely reversing our function like that isn't gonna actually get us there. How long have I been doing this now? We're at 45 minutes. I'm going to take a little break and use the bathroom, and we will pick this up. I do think this approach might be more fruitful than my prior one, even though I spent 45 minutes on it and still haven't really gotten anywhere. But we'll pick this up.